Hello future engineers, welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. That's one way you can keep me going, inspired and refreshed. Now, if you find my videos interesting and important to your studies, also please don't forget to subscribe. Problem 134. Water at 20 degrees Celsius of kinematic viscosity 1 times 10 to the negative 6 square meter per second and specific weight of 9.827 kilonewtons per cubic meter flows in a 250 millimeter diameter pipe at the rate of 60 liters per second. Compute the rate of energy lost or power lost in kilowatts due to pipe friction in a distance 600 meters for the following conditions. First, pipe is new commercial steel with roughness of 0.046 mm. So this is very small roughness. So we can assume that the pipe behaves as a smooth pipe. And let's verify that later by computing the thickness of the viscous sublayer. And B, pipe is rough concrete. E is 2 mm. So here we can assure that the pipe is behaving as fully rough. So we use Colebrook equations here to correspondingly solve for the friction factors. Then pipe is new galvanized iron with roughness of 0.15 mm. So this might be a situation where we have a transition from smooth to rough. Even in part A, we can assume that it is a transition from smooth to rough, but we will just investigate if the pipe can be considered as smooth pipe. Then the power loss or rate of energy lost is actually equal to weight flow rate Q times specific weight times the head loss. So for our solution, let's set up the formula for power loss as specific weight as weight flow rate Q times specific weight of water times head loss due to pipe friction. And this is by Darcy-Weisbach formula FL over D times velocity head. So it's really the friction factor that matters here to solve for this power loss, where friction factor is solved by using Colebrook equations, and velocity is 4 times discharge over pi diameter square. So this is the formula for by Colebrook if the pipe behaves as smooth pipe. 1 over square root of f equals 2 log quantity r sub e square root of f over 2.51. Then for the velocity, it is 4 times discharge 0.06006 times pi 0.25 square. So it is 1.2223 meters per second. So 4 times 0.06 over pi 0.25 square. So 1.2223 meters per second. Then the Reynolds number is diameter mean velocity over kinematic viscosity. So substituting 0.25 times 1.223 times 1 times 10 to the negative 6, the viscosity, kinematic viscosity. So 305,575. Then uh, we substitute into this formula here. So 1 over square root of f equals 2 log of 305,575 square root of f over 2.51. And using your high-tech calculator there, so f is 0.01441. So this is a low value that simply the friction factor for smooth pipe. Then the thickness of viscous sublayer, which is 14.14 times diameter over Reynolds number square root of f, or 14.14 times kinematic viscosity over quantity mean velocity square root of f. So we'll use the other formula, 14.14 diameter over Reynolds number square root of f, where this is in mm if the diameter is set to mm also. So 14.14 times 250 mm over 305,575 square root of 0.01441. It is equal to 0.09637 mm, which is greater than 0.046 mm. So that means we have verified that the pipe behaves as smooth pipe. Therefore, the friction factor is adapted here. So we can now compute head loss, friction factor, length, which is 600 over diameter 0.25, velocity head v square over 2g, 1.2223 square over 19.62. So the head loss due to pipe friction is 2.6335 meters. Then power loss can now be computed. Discharge 0.06 times specific weight 9.807 kilonewtons per cubic meter times 2.6335 meters. So this is in kilowatts and it is equal to 1.550 kilowatts. For the second pipe is rough. So the roughness is 2 mm. So this is indeed rough. So the pipe behaves as fully rough in this case. So therefore, 1 over square root of f equals 2 log quantity 3.7 over E over D. That's the formula for pipes that behaves as fully rough pipe. Then everything is known. So 1 over square root of f equals 2 log of quantity 3.7 over point over 2 mm over 250 mm. So computing for f is 0.03520. Then the thickness of viscous sublayer, just to verify, although it's obvious that the pipe behaves as fully rough, 14.14 diameter over Reynolds number square root of friction factor. So it is equal to 0.06166 mm, which is less than E over 14, which is 0.1429 mm. So indeed, the pipe behaves as fully rough because the thickness of viscous sublayer is less than E over 14, or absolute roughness over 14. You look at the video if you're still new or you're wondering where this 14 comes from. So it is explained there. So we have proven that the pipe behaves as fully rough, therefore we adapt this friction factor. So head loss is equal to 0.03520 times 600 over 0.25 times velocity head 1.2223 square over 19.62. So HF is equal to 6.4330 meters. Then power loss is Q gamma 0.06 times 9.81 times 6.4330. So power loss in kilowatts is equal to 3.785 kilowatts. Then part C, this may be the transition from smooth to rough. So Colebrook equation is 1 over square root of f equals negative 2 log of the quantity E over 3.7D, the reciprocal of this, then plus 2.51 over R sub E square root of f. So 1 over square root of f equals negative 2 log of quantity E over 3.7 diameter plus 2.51 over Reynolds number square root of f. So in fact, this is the formula that you should remember. Now for common pipes, commercial pipes, for example, when the roughness is 0.046, 0.15, as low as this, you always use this. You always use this. Even if the pipe behaves as smooth, we still use this when E is given, because this is by Colebrook equation, considering the transition from smooth to rough. So we substitute values and solve for f. 1 over square root of f equals negative 2 log of quantity 0.15 over 3.7 times 250 plus 2.51 over 305,575 square root of f. So using your high-tech calculator, f is 0.01873. And if you want to verify that this really falls between the transition from smooth to rough. Then let's solve for thickness of viscous subair, 14.14 times diameter 250 over Reynolds number 305,575, square root of friction factor 0.01873, and it is equal to 0.08453 mm, which is uh, less than E over 14 and greater than E over 14, greater than 0.15 over 14, but less than E. So 0.15 over 14 is which is 0.01071, is less than the thickness of viscous sublea, which is 0.08453, and 0.08453 mm is less than 0.15 mm. So this really proves that the pipe is in the transition from smooth to rough, and therefore we adapt this friction factor. Head loss therefore is 0.01873 times length 600 over 0.25 diameter, velocity head 1.2223 square over 19.62, and it is equal to 3.4230 meters. Then power lost is discharge 0.06 times 9.827 times 3.4230. Then power loss can now be computed, and it is equal to 2.014 kilowatts. Problem 135, gasoline at 20 degrees Celsius with kinematic viscosity 4.6 times 10 to the negative 7 square meter per second and specific gravity 0.68 flows in a 200 millimeter diameter pipe at the rate of 70 liters per second. Compute the friction loss per kilometer length of pipe if the pipe is smooth, the pipe is new wrought iron with roughness 0.046 mm, the pipe is new cast iron with roughness 0.26 mm, and the pipe is rusted steel with roughness, absolute roughness 2 mm. So for the solution, head loss by Darcy-Weisbach formula, FL over diameter, quantity, velocity head, where V can be computed, and the flowing fluid is gasoline, which is less viscous. Therefore, this is definitely uh, turbulent. The flow is turbulent, and then if we have pipes with roughness 0.046, 0.26, so definitely it is a transition between smooth and rough. And if we have a rusted steel pipe, which is 2 mm compared to 200 mm diameter, so this definitely is considered a rough pipe. So for the first part, the pipe is smooth, so we use Coolbrook equation for smooth pipes, which is 1 over square root of F equals 2 log of quantity R sub E square root of F over 2.51. But before that, let's solve for the mean velocity of flow. So this is the formula by Darcy-Weisbach, FL over dV square over 2G for head loss. And velocity is 4 times discharge, 0.07 over pi times zero point 0.2 square, diameter is 0.2 meter. So 2.228 meters per second. Then the Reynolds number, which is diameter mean velocity of flow over kinematic viscosity, 0.2 times 2.228 over 4.6 times 10 to the negative 7. So that's 968,696. That's the Reynolds number, which is high. Then we use Coolbrook equation for smooth pipe. 1 over square root of F equals 2 log of quantity R sub E square root of F over 2.51. So from here, we can solve for F using your calculator there. F is 0.01171, and from here, we can solve the head loss. So head loss is friction factor 0.01171 times 1000 meter per kilometer over diameter 0.2 times velocity head 2.228 square over 19.62. So the head loss is equal to, so that's the answer for part A, 14.81 meters. For part B, the pipe is new wrought iron. E is 0.046. So by experience, when the fluid is flowing, and these are the pipes involved, point something roughness, then always use the Colebrook equation for computing friction factor, which is a transition from smooth to rough. So 1 over square root of F equals negative 2 log of quantity E over the 3.7 D plus 2.51 over Reynolds number square root of F. So this is the formula that you should memorize. This is the only one formula that I recommend you should memorize, because for smooth pipe it is here. You just set this first term 0. For rough pipe, then you set this second term to 0. And for the most common case where we have roughness and Reynolds number involved contribute to the flow, so we have to contribute rather to the characteristics of pipe flow, whether the pipe is smooth or transition between smooth and rough or fully rough. So we always use this for problems involving pipes, and if the roughness of the pipes are given, and we should experience for roughness at these values here, which are considered low values compared to the diameter. So 1 over square root of F equals negative 2 log of quantity 0.046 over 3.7 times 200 plus 2.51 over 968,696 square root of F. From here, using your calculator, F is 0.01502, which is relatively low also. So HF equals 0.01502. So this is the formula. Length over diameter 0.2, velocity head. So let's express it in general in terms of F, and we'll use that as our formula, so that we'll just compute for F. So it is 1265.03 times F. So since F is known, so HF is 1265.03 times 0.0502. So HF is equal to 19.00 meters. Next is when the pipe is new cast iron, so we anticipate that it is a transition from smooth to rough, so we use this same equation. 1 over square root of F equals negative 2 log quantity 0.26 over 3.7 times 200 plus 2.51 over 968,696 square root of F. So solving for F, F is equal to 0.02121. Then substitute here, HF equals 1265.03 times 0.02121. So HF is equal to, so that's the answer to part C, 26.83 mm. So based on our experience, this pipe, which is rusted steel, the absolute roughness is 2 mm. So definitely this behaves as fully rough. So we use the formula 1 over square root of F, 2 times log of 3.7 over relative roughness, which is E over D. So 1 over square root of F equals 2 log of quantity 3.7 over E over D. So 1 over square root of F equals 2 log of quantity 3.7 over 2 over 200. And friction factor is equal to 0.03790. So from there, substitute here, HF equals 1265.03 times 0.03790. So head loss is equal to 47.94 meters. Then let's verify that our assumption for parts B and C were correct, that the pipe behaves as a transition from smooth to rough. So let's compute for the thickness of viscous sublayer, which is 14.14 times diameter over Reynolds number square root of F. So for part B, 14.14 times 200 mm over Reynolds number 968,696 square root of 0.01502, which is this. So thickness of viscous sublayer is equal to, that's the formula, so it is indeed equal to 0.02977, which is greater than 0.046 over 14, but less than 0.046. So our assumption is correct. Then for part C, 0.003649 over square root of 0.02121, it is 0.02506 mm, which is greater than 0.26 over 14 mm, and less than 0.26. So 0.26 over 14 is less than thickness of viscous sublayer, and thickness of viscous sublayer is less than this absolute roughness given. So that's the reason why our assumption for parts B and C were correct. And if you want to compute for friction factor or thickness of viscous sublayer for part B only, so A and D, there's no need to verify because for part A it is already a smooth pipe. Then for part D, the absolute roughness is very high, 2 mm, and it is definitely, the thickness of viscous sublayer is definitely less than 2 over 14, which is 0.14 something mm. So that's it, and I hope that you're able to understand the explanation, the formulas used, and you can remember the formula. I suggest that you just remember this formula here because this is the formula which is always applicable in computing for friction factors.